This video is on how to use Excel to do linear least squares. And this is a problem that we're going to encounter a lot in analytical chemistry, where we build a calibration curve and we want to use that calibration curve to analyze an unknown. So we're going to show how to do that. I'm going to show you how to do that in Excel. So this follows along with Harris's treatment in Harris's 8th edition of his book, and it is described on page 89, section 4-9, a spreadsheet for least squares. So I'm going to go through that, and we're going to look at, in the same edition of the textbook, exercise 4-G, which is on page 92. So in that problem, we're looking at the analysis of protein using a Bradford reagent. So Bradford reagent is something that's brown, but when you add it to protein, it turns blue. And then you can measure the saturation of that blue color, the absorbance of that blue color, and that will tell you something about the concentration of the protein in your sample. So Harris's convention is that we leave column A, so you'll want to open up Excel to do this. So we leave column A empty so that we can put constants and so forth there. So we're going to start our work over here in column B. But first thing I'm going to do is give this spreadsheet a little title. So I'm going to say calibration curve analysis, and maybe something else like protein. So if I ever look at this spreadsheet again, I'll know specifically what I'm talking about. And then I'm going to create a little table of data right here. So in this column, what I have is my standard protein sample, and that's going to be in units of micrograms. So I've dissolved a certain number of micrograms, of protein in some solvent. So I like that. I'm going to click check right here to accept that, and I'm going to select wrap text just so it kind of spreads that out a little bit. And I might even lengthen this column a little bit. So there's my standard protein, and then here's the absorbance. And absorbance is unitless, but I'm going to go ahead and make a note that it's at 595 nanometers. Good, so that's good. Wrap text. Expand that just a little bit so absorbance is all one word. Good, so now we've got a column to type in our data. So here's our standard protein. So our first sample didn't have any protein in it. And then the next ones I'm just going to type in the values. Then we're ready to enter the absorbance values. So presumably you've gone and done this experiment. You've measured the absorbance values, written those down in your lab notebook. So now we're ready to type those in, and here we go. Okay, so now we've got our data typed in. So here's our x variables. So this is the independent variable, the one that we control, and then we measured the response, the absorbance right here. So this is our x variable, this is our y variable. And so we might want to make a note of that up here just so we're clear on that. We can remind ourselves, this is our x data, this is our y data. So what we're going to do now is plot this data. So we want to make sure that this curve actually kind of looks linear. So what I'm going to do is just select this data, I'm going to go up here to the insert menu. We're going to insert a graph, and the graph we want to insert is a scatter plot. So select scatter plot. And we're just going to plot the points without any curves or lines drawn through them. So we're going to plot that. Okay, so here's our graph. Move that up here a little bit. So there's our graph, and yes, indeed, it is linear. So down here, this would be protein in micrograms and absorbance. So we're going to go ahead and add a trend line to this graph. There are a couple of ways we can do that. So up here in the layout area, you can select trend line and more trend line options, and then it will draw a trend line through your data. And down here you can say display equation on the chart and display the r² value on the chart. And then you can click and drag this label right here if it's in the way. So this data does in fact look pretty linear, and its r² value is really exceptional. We call that 3 nines on our r², 0.999, and then we get some other number, 8. And this gives us the equation of our straight line, slope plus intercept. So that's the information that we need. But it turns out that we want to calculate uncertainties in some numbers. So we're going to need a little bit more data than Excel will print out on the graph for us. So we're going to use another function that Harris talks about. It's called the linest function in Excel. So what we're going to do is right here underneath this x data, I'm going to select a little 2 by 3 block of cells. So you have to select it, and it has to be this number. So we're going to select that block of cells. Now up here into this area, this is where I can type my formula in the formula bar. So click in that. Now we're going to type a formula. So we're going to say equals. You always have to type the equals when you're entering a formula in Excel. And our formula is line st for statistics describing the line. So line st. So then you close the parentheses here, and notice up here it's told you a little bit about what the functions are. So the first thing that you're going to enter are the known y values. So here's the way that I enter the known y values. Find the y values, click on them, select them like that, and you're good. So now we type a comma, boom, and it switches over to the known x values. Now we're going to select those x values, so click and drag, and you've selected the x values, then a comma. Now the next thing is a constant. It says the constant will set b equal to 0. So b is your intercept. Do you really want that to be set to equal to 0? Well, not in our case, so we're not going to do that. So we're going to select this to true, where b is calculated normally. Alright, so we select true, and then we're ready to do the next thing, and then it says stats. So stats says return additional regression statistics. False says do not return additional regression statistics. Well, we want those extra numbers. That's why we're doing this. So we're going to set this to true, and you can either set this to true by double clicking this entry right here, or you could just type it in yourself, TRUE. Alright, and it doesn't have to be all caps either. And then you close the parentheses. Good. Now here's the tricky part. So make sure you do this. You're tempted right now to either click the check mark or hit enter, but we have to do this in a special way because we want to tell Excel that this is an array formula. So we want it to spit out numbers in a list, a table, and we call that in computer lingo an array. So what you're going to do is you're going to type control, the control key, the shift key, and the enter all at the same time. So you're going to type control, shift, enter, and hit that. Now, if you happen to be on a Mac, the sequence is command and return if you're on a Mac. All right, so that spits out some numbers. So what are these numbers? Well, Excel spits these numbers out in a particular way, and so Harris is going to have us label what these are. So M comes first, and I'm going to line that up so that it's over here on this side, like that. So that's M, that's your slope. Over here on this side, we have our B value, that's our intercept. This number right here is your S subscript M, so that is the standard deviation in your slope, which we can think of as a measure of the uncertainty in the slope. And you see, because there wasn't very much scatter in our data, there's very little uncertainty in our slope at all. Just to make this look a little bit nicer, what I'm going to do is select this M up here in my formula bar. Then I'm going to go up here to the font section of my home menu, and right here, this little tab right here, I'm going to click that. And down here it lets me make that a subscript. So I'm going to click on subscript. That's just going to make it look a little nicer. So now it's an S sub M value. I'm going to say, yep, check on that. And then we're going to move that so that it's lined up against the right side of this cell, just so it's next to this number and I can keep track. This right here then, by analogy, is going to be the standard deviation in our intercept. So by how much error is there in the intercept of this value. Oh, notice that the slope and intercept are the same that Excel generated in this equation up here. That's good. So we're going to do the same thing, subscript that, select it, go to the font menu, click on this little button to format our cells, and do subscript. There we go. OK. Click check to accept that, and it's lined up against the left edge next to that number. This number right here, this is our R squared value, so capital R and a 2. We're going to go select our 2, the font menu, click on that, and make it a superscript. So we check that, click OK, good, check mark, and we're going to line that up again against the right side of the cell. Then over here, this is S sub Y, so that's going to be the standard deviation in a Y value that you would predict from your X value. So if you just plug in any X value into this equation, you're going to calculate a Y value. What's the uncertainty in that Y value that you calculate? It'll be this number, so that's the standard deviation. So we're going to click this button right here, subscript that, so it just looks all nice and neat. Alright, very good. So this gives us our regression analysis for our calibration curve. Now the next part of this problem, we're going to go in and imagine now that we have a protein sample that we've measured, and we found out that it gave an absorbance of 0.973 absorbance units. So looking on this graph, 0.973 is going to be up here somewhere, so we read over and kind of down. Okay, it looks like it's going to be kind of in the 25% range, but we want to find that exactly. So how would we do that? Well, find it as precisely as we can. I shouldn't say exactly. We want to find it as precisely as we can. So we're going to use this equation. So we've taken a measured absorbance So we're going to plug that in as our y value because absorbance goes on this y-axis. And then we're going to solve that for x, and that will tell us what the corresponding x value is. And then we're going to need to know, well, what is the uncertainty in that x value, and what is a 95% confidence interval based on that standard deviation? So first we're going to need to calculate some other numbers. So we're going to go ahead and do that here in these cells. So right here I'm going to start calculating some other numbers that we'll need, and I'll explain where all this comes from in just a minute. Alright, so first we're going to calculate the number of data points that we had in our standard calibration curve. So to do this, we're going to type in a formula. We're going to say equals. That tells Excel we're going to do a formula, and our formula is going to be count. So count. And what we're going to do is count these values right here. So we're just going to select those and close our parentheses. So this is telling Excel, hey, count how many values you have here. So it turns out that this spreadsheet that you're making is very useful. Let's say later on you have another calibration curve. All you have to do is replace this x and y data with new data, and if you go in and decide to include some more points in your calibration curve, you just add more rows, and then when you're selecting this graph you're going to need to increase your x data and your y data, and you also have to change it here in linest, but you can just insert rows. So this is sort of a template that you can use then for doing this calculation. So that just tells us how many values we have in our calibration curve. We have 5 points. The next value that we need is the average of the y values in our calibration curve. So we need the mean y. So we're going to calculate the mean y. And so the way we do that is use another formula. So we're going to say equal, then we're going to say average. So just type out average. We can select it from that list, and then we're going to select the numbers that we want to average. So absorbance is our y value, so we're going to average those, close the parentheses, and accept that. So there's our mean y value. The next thing that we're going to calculate is called the squared deviation. And I'm going to go ahead and type in the formula here, and then we'll talk about what it means. So with this I'm going to do just a little bit of formatting. So I've typed it in, so s parentheses xi minus mean x parentheses 2. So what I'm going to do is select this S right here. I'm going to go to the font menu, and I'm going to actually select a different font. So I'm going to go down and select the symbol font, which is right here. The symbol font gives us Greek letters. So since I've selected the capital S here, that's going to make this a capital Greek letter sigma. Boom, there it is, sigma. And then right here I'm going to make this I a select it and make it a subscript like we've done before. And make this 2 a superscript. So I select it and make it a superscript. Okay. I'm good with that. Now what I'm going to do, just so we can see this a little bit better, I'm going to make my X column a little bit wider. There we go. So now let's talk about what this means. So this is called the square deviation, or the dev squared. And so what we're going to do is for each and every X value that we have in our calibration curve, we're going to subtract that from the mean of x. So we're going to take this average x value and we're going to subtract that for each and every one of those. And then the sigma right here is summation notation, so we're going to add all those up. So the first thing you're going to do is take 0, subtract from it the mean of these 5 numbers, and then you're going to square that. Then you're going to go plus 9.36 minus the average, that quantity squared, plus, and you keep on doing that. So that's a big pain to type in, but luckily this is a common function that gets used a lot, so Excel actually has a way of calculating that. So we're just going to type in Excel's formula. So we're going to type in equals, then we're going to go in and type dev squared, D-E-V-S-Q. Very good. And we want the square deviation in these numbers. So we're just going to select our x values, because these are all related to the x values. Close that parentheses and click check. And there's our deviation squared. Square deviation. Okay, so now we've got the numbers that we're going to need to do all that other stuff that I talked about. So down here we're going to type in a word measured y. And type in some other labels here. K, which is equal to the number of replicates. Good, and actually that's a little bit long, so we're going to wrap the text on that. Make our A column just a little bit wider. and then we're going to calculate our derived x value, our standard deviation in the x value, and finally our 95% confidence interval in x. Okay, so let's talk about all these things. So the measured y value is the y value of your unknown that you've measured. So you've gone out and you've measured the absorbance, in this case, that's what the y value is, for this protein. And I told you that that absorbance value is 0.973. That's the measured absorbance. And if we had actually mixed up several of those unknown samples, all the same, but different procedures when we've added the reagent and so forth, and measured replicates of that, then we would type in here our average absorbance. So we would measure like 3 or 4 or 5 absorbance values and enter the average in here. So down here, this is the number of replicates that you did when you measured the y. So in our case, we just measured 1. So we're going to type in a 1 here because we've just measured 1. But if you had measured several and averaged them, you would type in here the number that you averaged. Finally, we have our derived x. So we're going to calculate it from this equation right here. So let's think about how you would solve this equation right here. So y equals the slope times x plus the intercept. So what we need to do is have y minus the intercept, right? So we're going to subtract the intercept from both sides. So that's going to be y minus b. And then we're going to divide both sides by m. And that's going to give us the x value. All right, so let's implement that in Excel. So we're going to use a formula to do that. So that equals what? Well, it equals our y value. So our y value is this entry right here. That's what we measured, our measured y value. Then we're going to subtract from that, so I type a minus sign, our intercept. So our intercept value is right up here. So I'm going to click that. We're going to close parentheses, and then we would divide by the slope to get our value of x. So our slope's right here, so I'm going to hit the slash for divide, and then we're going to just click on this slope entry right here, cell B10, and that's going to calculate our derived x value. Boom. All right, so 23.07 blah blah blah, right? So remember we looked up here and we said 0.937. That's going to be, and I said around 25, so I was a little bit off, but you know, 23, so that's in the ballpark. So that's a good check. You want to do that visually to make sure that the number agrees and that you haven't made an error in your formulas somewhere. Okay, so now we want to calculate the standard deviation in x. So let me go ahead and make that a subscript just so it looks nice and neat here. Okay, so now we're ready to calculate the standard deviation in y. And that, it turns out, is a pretty complicated formula. And here it is. So this comes from Harris. So the uncertainty in an x value, which is your standard deviation in x, comes from this fairly horrific looking equation. So this thing right here is the standard deviation in the y value. And lo and behold, look, Excel has given that to us, Linest has given that to us. Down here, this is the absolute value of the slope. So if your slope were negative, you would want to take the absolute value of that. And then you have the square root of this whole quantity. So first, 1 over k. What is k? K is the number of replicates in your measured y value, right? So if you have more replicates, you're going to be more certain about your derived x value. Then 1 divided by n. N is the number of points in your calibration curve. Then up here, what is this? This y is your measured y value. So that's going to be this number right here. That's the number that you measured, minus the average y from your calibration curve. So that's why I calculated this number right here, our mean y. So that's what this means. With the overbar, that means mean. So we're going to take our measured value, we're going to subtract from that the mean value and square that. Then down here, we're going to divide by m squared, so that's just your slope squared. And this summation right here, well, that's just the square deviation that I talked about. So the deviation of x from its average squared, and we add up all those. So the sum of the square deviations. And so we have that number already. So now we just need to type this formula carefully into Excel. So what I'm going to do is bring this window down a little bit. Okay, so we're typing in an equation, so the first thing we type is equals. Okay, so now it's going to be SY, so our standard deviation in y, so that's that number, divided by the absolute value of our a slope. So we're going to type in ABS for absolute value, parentheses. Then we're going to click here for slope, close parentheses. Okay, now we're ready to multiply by this square root. So we hit a times here. Now order of operations means that this time is not going to be in the denominator down here. So times, then we need to take the square root of everything inside of here. So I'm going to type SQRT for the square root function, open parentheses. Now I need to type in all this stuff. So to keep track, I'm going to use parentheses. So parentheses, so I'm going to type in this term right here. So that's 1 divided by k. Where's k? And it's right here, k. So I'm going to click that cell, that's my k value. Close parentheses, so that's that term. So then plus this term, so I'm going to open another parenthesis and say 1 slash for divided by n. So what is n? That's right here, that's the number of data points in my calibration curve. So that's that term. Then we're going to say plus, and then up here in parentheses I need to do this term, so I'm going to have a parenthesis here. So we're going to say y, what's my y value, measured y, this, minus, then we want to have the y value averaged, so my average y is right here, the mean y. Click that, and I close my parentheses, so that's closing this parenthesis right here. Then I need to square it. So you hit the caret key, which is right above the number 6, so you go Shift 6, that will give you this little caret symbol, and then you can just type in a 2 to square that. Now we need to divide, so I'm going to have my slash here. We've got a bunch of stuff we need to divide by, so I'm going to put parentheses around this whole denominator so we don't end up with order of operations issues. So the first thing I need is my slope squared. So I'm going to click on that value, then do again Shift 6 to get the caret, 2 for squared, and then that's going to multiply this sum of the square deviations. So I hit the asterisk key, star for multiply, and so that's either on your numeric keypad or you can hit Shift 8 to get that. And then we're going to type in our dev squared. So where's that? That's cell B16 right here. So I put that in. And now I can close my parentheses for the denominator. Boom. Okay, now I need to close my parentheses for the square root. Boom. Okay, so I've done that. And that's everything. So now I'm ready to hit check. There we go. So there's my standard deviation in X. Now we're ready to calculate the 95% confidence interval. So there's a formula in Excel for there's a formula in Harris for calculating confidence intervals, but we are going to use Excel to do that for us. So a confidence interval is going to be equal to, so it's the value off of the t-table for the right number of degrees of freedom. So I'm going to tell you what that is. So what we're going to do is, actually I should warn you that things are a little bit different in this formula because we are getting our data from a calibration curve rather than from a set of data. So we've taken a measured y and we're finding our x value out of this calibration curve. So the way we calculate that is to take the t value for n minus 2 degrees of freedom, and then we're going to multiply that by the standard deviation in x. So the first thing that we're going to need is the t value for 2 degrees of freedom. So what we're going to do is TINV. This is T inverse. And it says this function is available for compatibility with Excel 2007 and earlier, and it returns the two-tailed inverse of the student's t distribution. That's what we want. It doesn't matter that it's for 2007. So we're going to select that. So first it says the probability. So this is where we set our confidence interval. And so this is actually the probability that we're outside of the area. So if we want the 95% confidence interval, then there's a 5% chance that we're outside of that. And so we're going to use 0.05 as our confidence interval. Then we put a comma. And then our degrees of freedom. So our degrees of freedom is n minus 2 degrees of freedom, where n is the number of points in our calibration curve. So the way we can calculate that is use our count right here. That. We're going to say minus 2. So why is it minus 2, you might be asking? Well, that has to do with the fact that in the equation for this line, we have calculated a slope and an intercept. And we use those two numbers to calculate our x value. So that has sort of removed 2 of our 5 variables because we have some remaining variables that are left, but we've got 2 that are derived from them. So we're subtracting off those 2 degrees of freedom. Then close that. Okay, so there's our t-inverse. Then we're going to multiply that by our standard deviation in x. That's that number right there. We click check, and we're done. So that tells us that we are 95% certain that the true value of protein content in this sample is going to be 23 point. And now we need to look at our significant figures. So our first uncertainty occurs in the 10th place. So we're going to report our derived x to the 10th place because that's where our first uncertainty occurs. So we're going to round this to 23.1. And so our final value is going to be 23.1. So we are 95% certain that we are plus or minus 0.9 of the value 23.1. So that's how we do calibration curves, calculating confidence intervals, and using line est function.